Welcome everyone to our work on an approach to ontological learning from weak label. This work is being presented at 2023 ICASSP. Myself, Ankit Shah, and here are my collaborators along with Professor Bhiksha. The outline of our presentation is as follows. First, we'll be introducing the problem, looking at importance of ontology, the task and its definition, approaches that we did in this work, and some results and key takeaways from our work. Ontology, as we know, encompasses a formal representation of knowledge through the definition of its concepts, properties of the domain, and the relationship between the concepts. So in this particular case, dog and people are related to animal with a is a relationship. People is related to car with an operate relationship. So as we can see that in this particular case, the ontology information is very valuable, and it has already been known to be successful for zero-shot learning on image classification and knowledge graph completion domains. And the importance of ontology helps in order to establish efficient annotation, better representation between the different classes, and thereby the ontology can help to understand what the hierarchy and relationships are there between these classes. For example, barking sound is a part of animal sound, is a part of natural sound. So this ontology information would help in order to bring semantic understanding to these machine learning models that we learn for classification tasks. So let's look at what type of data we are working with. In this particular work, we look at weakly labeled data, which means that we have audio file that contains only the information about whether an event is present in the data or not, but we don't know what timestamp information the event is present. So in this case, we know that there is laughter, barking, siren, which is present, but we don't know where it occurs. And this is the example of an ontology, audio ontology, where we have the we have the superclasses to be human sounds, animal, music, etc. And then there are subcategories of sound within these superclasses. So what do we infer as humans from ontology? Let's say if we are given this recording, then we would say that this recording would contain 3 dog barks and a person that is speaking. And as humans, we'll be able to also understand that this audio clip contains animal sounds and human sound as higher level label, rather than saying that this contains nature sounds, for example. So what is this paper about? We want to utilize this ontological information to better infer the hierarchical class from weakly labeled data. And as we know that this domain knowledge can be very useful to better understand weak labels, so it is an active area of research problem in this particular space. So the task is where we have audio set that is consisting between the is a relationship through different ontology classes. We extract 2 top level classes with 42 subclass and 7 superclasses. We use this standard training and evaluation setup and extract 128 VGG dimension embeddings in order to represent the audio. The task is then to predict the ontology labels from the top 2 levels of the ontology in the audio set. And we do this formally using where we describe this as X1, Y1 pairs, where X1 is essentially consisting of the audio as feature representation. Y1 is a collection of labels where each of the labels are at each of the individual ontological levels. So here we process the data with k equal to 2, where we have the subclass referred to as level 1 and superclass referred to as level 2. So the approach that we take is, first we implement a simple MLP with 3 hidden layers in order to predict the both ontological classes. The other is we implement a twin neural network architecture model where we separate the ontology embedding by imposing an embedding distance, where the embedding distance is close to 0 for same subclass, and it is 1 for different subclass but same superclass, and close to 2 for different superclass. And we use the standard binary cross entropy loss and sigmoid activation for multi-label dataset. So here, as we see that we have the MLP to learn the feature representations, on top of which we relate the probability between the PY1 given X, and PY2 given X is related with the ontological layer M which relates the different class probabilities amongst the levels. And M here will average the probability of the subclass within a superclass. And the loss function is defined to be the loss of the level 1 and level 2, along with the embedding loss, which is essentially the difference between the embeddings that are being learned through the MLP with the imposed constraint. Further, what we do is that instead of using an ontological layer, we represent the ontological layer information using a graph convolution network, as GCNs are known in order to better represent the relationship between the embeddings. So here we use two GCN layers in order to extract the neighboring information to model these relationships. And the correlation matrix was established in order to understand which layers are connected with one another within the twin neural network architecture. So what we see is that our results showcase that an MLP with a GCN actually outperforms even the twin neural network with GCN, which was a bit surprising. And there are some reasons that we will cover in the discussion section. So the similar trend was also observed at the lower level labels as well, where we identified what each of the individual mean average precision scores and the AUC scores represent for twin neural network with ontology and MLP with ontology. So in case of the MAP scores for the super level labels, we find that an ontology with GCN is hard to improve over just a simple MLP to learn the embeddings. And some of the reasons why this would occur is that in case of twin neural network architecture, the focus is on a single label dataset, but whether audio set is actually a multi-label dataset. So what I mean by this is that let's say if we have clip with dog, car, and car alarm, and another clip with dog, wind, and raindrop, then the model may not be suitable if the two clips are having exactly the same labels, or whether we should consider that the two clips that contain exactly the same labels, but there is an intersection between the labels. So the definition 2 actually performs better. The model with TNN and GCN performs better than just the ontological layer, because GCN is capable of having the co-occurrence relationship as well as perform better in case of noisy labels for audio set. What we find is that just having a simple MLP with a GCN layer is capable of performing equivalent to what a TNN with GCN is performing. And we found that the TNN network overall is not significantly important for case of single label classes. And the key takeaways here are that the TNN with ontological layer has like the worst performance, while the MLP has the better performance. And this is possible because the TNN would have a negative impact on the prediction due to the confusion between the input pairs when the data is weakly labeled, whereas a GCN provides significant importance and it appears to be more useful in the learning process. However, the model still has difficulty when there is ambiguous subclasses that are present or using any hidden knowledge within the weakly labeled data. So for future work, what can be done is that additional or deeper level of layers of the ontology can be used in order to better model the ontological information. However, this work represents that ontology information does help in order to learn better hierarchical classification and relationships between the audio classes, and it's an important direction of research in weakly label setting. Thank you, and we welcome any of your questions.